In this lecture, we're going to talk about solving linear first-order ordinary differential equations using integrating factors. Alright, before we start the actual lecture, I want to start with a warm-up problem. So let's find the derivative of e to the 2x times y with respect to x. So pause the video, take a moment, see if you can find this derivative. Alright, so to take this derivative, we're going to use the product rule. So the product rule says we can take the first, e to the 2x, times the derivative of the second, so that'll be the derivative of y, plus the second, so that's y, times the derivative of the first, so the derivative of e to the 2x. So if we simplify those, we're going to get e to the 2x times y prime plus 2e to the 2x times y. All right, so that'll be the derivative of the product of e to the 2x times y. So keep this in mind. This is going to show up again in just a few moments, so keep this in mind, all right? All right, so let's begin with the definition. Our first order differential equation of the form a1 of x times the first derivative of y with respect to x plus a naught of x times y is equal to g of x is going to be a linear equation in the dependent variable y. So this matches up with what we've talked about with linearity. Y and its derivatives have a power of 1, and the coefficients all depend on x's, not on y's. So that satisfies the linearity properties that we talked about previously. And so if we have a linear equation, we can classify it. If the right-hand side is equal to 0, so if g of x is equal to 0, that's called a homogeneous equation. And if the right-hand side is not equal to 0, then it's a non-homogeneous equation. All right, so we're going to want to put our linear equation into standard form. And the standard form of a linear first-order ODE can be found by dividing everything by that leading coefficient a sub 1 of x. So if I divide everything by a1 of x, then the dy dx is left alone, so it has a coefficient of 1 now. I get p of xy, where p of x is a naught divided by a1, is equal to f of x, where f of x is the g of x function divided by a1. So if I want to find the standard form of a linear first-order differential equation, essentially I'm just going to divide the whole equation by whatever the coefficient of dy dx is. All right, so if we want to solve a linear first-order differential equation, we're going to use what's called an integrating factor. So we're going to take the following steps. First, we're going to find the standard form of the linear equation. So that means we're going to divide everything by the leading coefficient. Second, we're going to use the p of x, so that's the coefficient of y, from the standard form to create an integrating factor. So our integrating factor, mu of x, is defined to be e raised to the integral of p of x times dx. Once we have our integrating factor, we're going to multiply all of the terms of our standard form by that integrating factor, and the left-hand side of the resulting equation is automatically going to be reduced to become the derivative of our integrating factor times y. So that means after we multiply through by our integrating factor, we can rewrite the left-hand side as the derivative of that integrating factor times y, and then on the right-hand side we would still have our integrating factor times whatever f of x was. All right, this is an important part of the process that isn't necessarily straightforward. It's something you just need to remember how to do. And then finally, we're going to integrate both sides of the equation, and we're going to solve for y. So let's jump right into an example. We want to solve y prime plus 2y is equal to e to the 3x. So the first thing that we need is we need this to be in standard form. It's already in standard form, so we can move on to forming our integrating factor. P of x is the coefficient of y, so in this term our p of x is just going to be 2. So we can use that coefficient to form our integrating factor. So mu of x will be e raised to the integral of 2 dx, and if we take that integral, that'll become e to the 2x. So our integrating factor for this problem will be e to the 2x. The next step in the process is to multiply everything by the integrating factor. So I get e to the 2x times y prime plus 2e to the 2x times y equals e to the 3x times e to the 2x. Now, if we look at the left-hand side of this equation, that should look familiar. E to the 2xy prime plus 2e to the 2xy, that was the result from our warm-up problem. So we know from our warm-up problem that this sum is going to be the derivative of e to the 2x times y. Right? So based on the product rule, whenever we're working with one of these problems that deals with integrating factors, the left-hand side is always going to be rewritten as the derivative of your integrating factor times your dependent variable. So again, the derivative of the integrating factor times the dependent variable. And then the right-hand side we can simplify to be e to the 5x. Now that we've simplified everything, we'll finish the problem by integrating and then solving for y. So if we integrate both sides of the equation, we get the integral of the derivative of e to the 2x times y with respect to x equals the integral of e to the 5x with respect to x. On the left-hand side, the integral and the derivative will cancel each other out, so we just get e to the 2xy. And on the right-hand side, we'll get 1/5 times e to the 5x, and we'll add our arbitrary constant over there on the right-hand side. So we get e to the 2xy plus, e to the 2xy equals 1/5 e to the 5x plus c. So the final step here would be to get y by itself if we're looking for an explicit solution. So we'll divide everything by e to the 2x, and that's going to give us y equals 1/5 e to the 3x plus c times e to the negative 2x, or c divided by e to the 2x if you prefer to write it that way. All right, so for this solution, typically our solution will have different terms. The term that has the arbitrary constant, that's the solution to the homogeneous part of the equation. So that means if I plug that term into my differential equation, it'll give me 0. And then the other term, the term that has an actual value, the 1/5, that's the solution to the non-homogeneous part. So if I plug that in, that's what's going to lead to the right-hand side of e to the 3x. Now this isn't important right now. This will become more important as we move through the course, but I just wanted to throw that out there so that you're aware of how these solutions are composed. All right, a little bit more terminology. So once we find the solution to our differential equation, any term whose contribution to the solution becomes negligible as x approaches infinity is called a transient term. So from our previous example, if we think about that solution, y equals 1/5 e to the 3x plus c times e to the negative 2x, if we let x tend towards infinity, so if we let x get really, really large, 1/5 e to the 3x is going to get really, really large. But if I look at c e to the minus 2x, remember that negative sign means we can consider that being in the denominator, so that's the same as c divided by e to the 2x. And if e to the 2x were in the denominator, then when x goes to infinity, that overall term, that fraction, is going to get very, very small. So this is going to tend towards 0, and so that means that c e to the minus 2x is going to be a transient term. All right, another piece of terminology, so any point that makes the leading coefficient, a1 of x, equal to 0 is going to cause a discontinuity on p of x, because we divide by a1 to get p of x, right? So anytime that a1 of x is equal to 0, that causes a discontinuity, and so that point is going to be called a singular point of the ODE. And singular points help to advise us what intervals we need to look at when we're considering the solutions to our differential equations. All right, so let's look at another example where we're going to pull in singular points and transient terms. So this time, we want to solve x times dy dx plus 2y is equal to 3. We want to identify any singular points and then the interval of existence of our solution. And we want to determine any transient terms when we're finished. So the first step to solving a first-order linear ODE is to put it in standard form. So we're going to divide everything here by x. So that's going to give us dy dx plus 2 over x times y equals 3 over x. Now that this is in standard form, we can identify the coefficient of y, so that'll be our p. So p of x is equal to 2 over x. Now note that when x is equal to 0, we get a discontinuity. So that means x equals 0 is going to be our singular point, And so we'll consider our solution on the interval from 0 to infinity. We can use our p of x to create our integrating factor. So mu of x is equal to e raised to the integral of 2 over x dx. If we take that integral, that's going to be e raised to the 2 natural log x. We can manipulate this. We can move that 2 from a coefficient inside the natural log as an exponent using the properties of exponents. So this becomes e to the natural log of x squared. And then when it's written like this, the e and the natural log will cancel each other out since they're inverses, and that'll just give us x squared. So our integrating factor for this problem is going to be x squared. We multiply the standard form of our equation by that integrating factor. So we get x squared times dy dx plus x squared times 2 over xy equals x squared times 3 over x. And now we want to simplify. Remember, the left-hand side on these problems will always simplify to be the derivative of your integrating factor times your dependent variable. So for this problem, that'll be the derivative of our integrating factor, x squared, times our dependent variable y. And again, that's because of the product rule. If we take this derivative, the derivative of x squared times y, we'll see that it gives us what we started with above. And then on the right-hand side of the equation, x squared times 3 over x simplifies to be 3x. Now that everything is simplified, we can integrate. So we take the integral of the derivative with respect to x of x squared y with respect to x. Then we integrate 3x with respect to x. On the left-hand side, the derivative and the integral will cancel out, so we get x squared y. And on the right-hand side, using the power rule, we'll get 3x squared over 2, and we'll add our arbitrary constant plus c. The final step here is to get y by itself to find an explicit solution, so we'll divide everything by x squared. So that gives us y equals 3 halves plus c divided by x squared. And if we examine our solution, you notice the x squared in the denominator of the second term. So that means when x goes to infinity, that second term is going to go to 0. So that'll be a transient term. So c over x squared is going to be a transient term. Now let's look at a third example. So this time, we want to solve cosine squared x times sine x times the first derivative of y with respect to x plus cosine cubed of x times y is equal to 1. Again, the first step that we take when we're solving these first order linear ODEs is we put it in standard form. So we're going to divide everything by that leading coefficient, cosine squared x times the sine of x. That's going to give us dy dx plus cosine x over sine x times y equals 1 over cosine squared x sine x. Now that we have this in standard form, we can rewrite using trig identities. So using the quotient identity, cosine over sine is equal to cotangent. So we get dy dx plus cotangent xy equals 1 over cosine squared x sine x. So p of x is going to be the cotangent of x, and that's going to have a singular point anywhere where sine of x is equal to 0. So 0, pi, 2 pi, 3 pi. So we'll consider our solution on the interval from 0 to pi. And we can use our p of x to create our integrating factor. So mu of x is going to be e raised to the integral of cotangent x dx. The integral of cotangent x dx is going to be the natural log of the sine of x. All right, so you can compute that by rewriting cotangent as cosine over sine and using u substitution, or maybe it's something that you already know from past experience. All right, so e raised to the natural log of sine x, our e and our natural log will cancel out. So that's just going to leave us with sine x. So our integrating factor for this problem is going to be the sine of x. We'll multiply everything in our standard form by this integrating factor. So sine x times dy dx plus sine x times cotangent x times y is going to equal 1 over cosine squared x. And then we're going to simplify. So again, that left-hand side is going to simplify to be the derivative of the integrating factor times the dependent variable. So that'll be the derivative of the sine of x times y. And then the right-hand side, 1 over cosine squared, we can rewrite as secant squared. Now that we've simplified, we can integrate both sides. And when we take those integrals, we're going to get sine of xy on the left-hand side. And the integral of secant squared is just going to be tangent. So we get tangent x plus c on the right. Our final step here would be to divide everything by the sine of x in order to get y by itself. So y is going to be 1 over the sine of x times the tangent of x plus 1 over sine of x times c. And if we simplify those using some trig identities, we're going to get y equals secant x plus c times cosecant x. And secant and cosecant, neither of one of those will trend towards 0, so there are no transient terms for this problem. All right, let's look at one final example where we're going to solve a first-order linear differential equation using an integrating factor. So for this example, we've changed things up a little bit. Our dependent and independent variables have switched. So we have y times dx dy minus x equals 2y squared, where with the initial condition of y of 1 is equal to 5. Okay? So now y is our independent variable and x is our dependent variable. The first step that we're going to take to solve this equation is we're going to put it in standard form. So we want that derivative to have a coefficient of 1. We'll divide everything by y. So dx dy minus 1 over yx equals 2y. Now that this is in standard form, we can identify the coefficient of our dependent variable. So p of y this time is going to be negative 1 over y. And note there'll be a singular point at y equals 0. All right, so since p of y is negative 1 over y, we'll consider our solution on 0 to infinity to account for that singular point. And then we'll use that p of y equals negative 1 over y to create our integrating factor. So our integrating factor will be e raised to the integral of negative 1 over y. We integrate that, we get e to the negative natural log of y. We can move the negative 1 that's a coefficient into the logarithm by making it a power. So we get e to the natural log of y to the minus 1. And then the e and the natural log will cancel out, so we'll get y to the minus 1, or 1 over y. So our integrating factor for this problem is going to be 1 over y. We're going to multiply our standard form by that integrating factor. So 1 over y dx dy minus 1 over y squared x equals 2. Then we're going to simplify. So our left-hand side, as always with these problems, will simplify to be the derivative of our integrating factor times our dependent variable. So for this problem, that'll be the derivative of our integrating factor, 1 over y, times our dependent variable, x. And that's going to equal 2 on the right-hand side. Now that we've simplified, we can integrate both sides. So we take the integral of the derivative of 1 over y times x with respect to y, and we take the integral of 2 with respect to y. So this gives us 1 over y times x equals 2y plus c. We're going to multiply everything by y to get x by itself. So x is going to equal 2y squared plus cy. So this will be the solution to our differential equation. But since this was an initial value problem, we have a couple more steps to take. We need to figure out what c is. So remember, they gave us this initial condition, y of 1 equals 5. So we need to apply that to this solution to figure out what the value of c is. So if y of 1 equals 5, that means x is 1 when y is 5. And we'll plug that into our solution. So if x equals 2y squared plus cy, then 1 will equal 2 times 5 squared plus c times 5. So 1 equals 50 plus 5c. We subtract 50 from both sides, so negative 49 equals 5c. And then divide by 5 to get c equals negative 49 over 5. Now remember, once you find this arbitrary constant, once you find the value of that constant, you have to plug it back into your solution. So our overall solution is going to be x equals 2y squared minus 49 over 5 times y.